Every time you look at the night sky, you are looking into the past. The light reaching your eyes from the moon left its surface about 1¼ seconds ago. The light from the sun is 8 minutes old by the time it warms your skin. The light from the nearest star beyond our sun has been traveling for more than 4 years. And the faint smudge of the Andromeda galaxy, just barely visible to the naked eye on a clear dark night, is carrying light that left its source 2.5 million years ago, before our species existed. The night sky is not a flat backdrop of simultaneous points. It is a window into many different moments in the history of the universe, layered on top of each other, each point of light a message from a different depth of time. Tonight, we are going to follow those messages outward, from the familiar distances of our solar system, through the silence between stars, across the vast structure of the Milky Way, into the galaxy clusters and cosmic filaments that make up the largest structures in existence, all the way to the edge of what the James Webb Space Telescope has revealed, where the universe as it exists today is hidden behind 14 billion years of travel time. We will move through these scales slowly and without urgency. There is no destination to reach tonight, only distances to appreciate. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. Settle in. Let your body rest. We are going to take our time. Chapter 1. The Scale of a Human Life. Before we can understand the scale of the universe, we need to understand the scale of a human being, not in an abstract or philosophical sense, but in a very literal physical one. We need to start where we actually are, with the body, with the immediate world, with the distances our senses were built to navigate. You are, on average, somewhere between 1.5 and 2 meters tall. Your arms, when stretched wide, span roughly the same distance as your height. From the tips of your fingers to the center of your chest is approximately 1 meter. The length of your stride when walking is about 3/4 of a meter. Your hand, spread wide, spans roughly 20 centimeters. The distance from your elbow to the tip of your middle finger, a unit the ancient world called a cubit, is approximately 45 centimeters. These are the measurements that feel natural. They are the units our bodies have always used to navigate the world around us. For most of human history, distance was measured in body lengths. A foot was a foot, literally, the length of a human foot. A cubit was the distance from elbow to fingertip. Even the word mile comes from the Latin phrase mille passuum, meaning 1,000 paces. The distance a Roman soldier could walk in 1,000 double steps, approximately 1,500 meters. We built our understanding of the world around the human body because the human body was the most reliable measuring instrument we had for most of our history. And for a very long time, that was enough. The village you lived in, the fields you farmed, the river you walked to each morning, all of these existed at a scale a human being could traverse in hours. Even the largest ancient cities, the sprawling capitals of great empires, places like Rome or Babylon or Chang'an, at the height of their power, were places a person could walk across in an afternoon. The world was large enough to be interesting and small enough to be navigable on foot. Then we started measuring more carefully, and the world grew. The circumference of the Earth was first calculated with remarkable accuracy by the Greek mathematician Eratosthenes around 240 BCE. He had learned that on a particular day each year, the sun shone directly down a deep well in the city of Syene in southern Egypt, meaning the sun was directly overhead at that location on that day. At the same time, in Alexandria, several hundred kilometers to the north, a vertical stick cast a measurable shadow. The angle of that shadow told him how far the sun had moved from directly overhead at Alexandria, relative to Syene. Using geometry, Eratosthenes reasoned that the angle of the shadow, approximately 7 degrees, represented the same fraction of the full circle of the Earth as the distance between the two cities represented of the Earth's total circumference. He multiplied accordingly and calculated that the Earth was approximately 40,000 kilometers around. He was correct to within a small margin of error. He used nothing more than a stick, some shadow measurements, a known distance between two cities, and careful reasoning. No spacecraft, no satellite imagery, no modern instruments of any kind, just geometry and patience. 40,000 kilometers. That number already begins to stretch the imagination a little. If you walked at a brisk pace without stopping, day and night, it would take you roughly a year to circle the planet once. Most of us will walk over an entire lifetime, somewhere between 100,000 and 200,000 kilometers in total, which means a single circumnavigation of the Earth represents perhaps a quarter of everything your legs will ever carry you through in a full lifetime of movement. That is the first scale to hold in your mind tonight. The Earth is 40,000 kilometers around. A human lifetime of walking could circle it perhaps 4 or 5 times. It is a large number, but it is still a number we can almost feel, almost grasp. We can imagine a year of walking. We can imagine the accumulated distance of a lifetime of steps. These numbers are large, but they are not yet beyond the reach of intuition. The distances we are about to encounter will require a different kind of patience entirely. There are places on this planet that most humans will never visit. The deep ocean floor, several kilometers beneath the surface of the sea, where the pressure is crushing and the darkness is absolute. The high Antarctic plateau, where the air is thin and the cold is extraordinary, and the nearest other human being might be hundreds of kilometers away. The remote interior of the Siberian taiga, where forests stretch to the horizon in every direction without a road or a building or a light to be seen. These places are separated from your front door by distances of several thousand kilometers. They feel impossibly far. They are, by any practical measure, unreachable without significant effort, planning, and technology. And yet, in the context of what we are about to explore tonight, they are right next door. Everything on this planet, every mountain range, every ocean basin, every city and forest and desert and ice sheet fits within a sphere roughly 12,700 kilometers in diameter. That is the size of the Earth. Not the circumference, but the diameter. The distance straight through from one side to the other, passing through the center. If you could somehow shrink the Earth down to the size of a standard basketball, the distance from the surface to the center would be approximately the width of your palm. Every human being who has ever lived, every war ever fought, every language ever spoken, every species we have named and countless more we have not, every ocean and mountain and city, all of it on the surface of something the size of a basketball in the right framing. This is where we begin tonight, right here, on a basketball-sized world, in a solar system we have not yet left, in a galaxy we cannot yet see the edge of. Everything else we will encounter tonight is larger than this. Chapter 2. From your doorstep to the sky. There is a layer of air surrounding this planet that makes everything we know possible. Without it, the surface of the Earth would be exposed to the full intensity of solar radiation, ultraviolet light that would break apart the complex molecules on which life depends. Without it, the temperature of the surface would swing wildly between extremes, scorching by day and plunging far below freezing each night, with no atmospheric blanket to retain the sun's warmth after dark. Without it, there would be no weather, no rain, no rivers, no liquid water cycling continuously between ocean and cloud and land. The atmosphere is so fundamental to life on this planet that it is easy to take it for granted. It is invisible. It has no obvious edges when viewed from the ground. It simply exists. The air we breathe, the sky we look up at, the blue color of the daytime sky produced by the scattering of sunlight through the gases surrounding us. But the atmosphere has a structure, and understanding that structure is the first step in moving from the surface of this world toward everything beyond it. The layer we live in, the troposphere, reaches from the ground to roughly 12 kilometers above sea level. All of our weather happens here. Every cloud, every rainstorm, every thunderstorm and snowfall and gentle morning fog exists within this layer. The air in the troposphere gets colder with altitude at a rate of approximately 6.5 degrees Celsius per kilometer. By the time you reach the top of the troposphere, the temperature has dropped to around minus 55 degrees Celsius, 12 kilometers. That is the altitude at which commercial aircraft cruise when carrying passengers across oceans and continents. When you look out a plane window and see clouds spread across the landscape far below you, soft and white and impossibly distant looking from above, you are near the top of the troposphere. You are near the ceiling of all weather. Beneath you is everything the sky has ever done. Every storm and sunrise and season that has ever touched the surface of this world. Above the troposphere, the atmosphere continues in layers of decreasing density. The stratosphere extends from roughly 12 kilometers to about 50 kilometers altitude. Within the stratosphere sits the ozone layer, a thin concentration of ozone molecules that absorbs the sun's most damaging ultraviolet radiation. Without the ozone layer, the surface of the Earth would be largely hostile to the complex organic molecules on which life depends. The mesosphere extends from 50 kilometers to approximately 80 kilometers. This is the layer where meteors typically burn up as they fall inward through the atmosphere. The streaks of light we call shooting stars are not stars at all. They are small fragments of rock and metal, most of them no larger than a grain of sand or a pebble, vaporizing in the friction of atmospheric entry somewhere in the mesosphere. The brief light they produce, lasting a fraction of a second, is the last moment of something that has been drifting through the solar system for billions of years. The thermosphere extends from 80 kilometers to roughly 500 kilometers altitude. The International Space Station orbits within the thermosphere at an average altitude of approximately 400 kilometers. From the windows of the station, astronauts can see the complete disk of the Earth below them, the curve of the horizon visible in every direction, the thin blue line of the atmosphere lying against the curvature of the planet like a barely there veneer, the shadow of night sweeping steadily across the continents below. That thin blue line is everything. Everything alive on this planet exists within it or depends upon it. It is roughly as thick, relative to the Earth's diameter, as the skin of an apple relative to the apple itself. It is astonishingly fragile looking from the outside. The atmosphere does not end at a sharp boundary. There is no wall, no sudden transition from air to space. The thermosphere gradually thins into the exosphere, which blends slowly and imperceptibly into the near vacuum of interplanetary space, somewhere around 10,000 kilometers above the surface. By international convention, the boundary of space is placed at 100 kilometers, the Kármán line, a threshold that represents the altitude at which the atmosphere becomes too thin for an aircraft to generate meaningful lift. 100 kilometers. If you could drive a car straight upward at highway speed, you would reach the edge of space in approximately an hour. It is a disarmingly short distance. The space between you and the vacuum of the cosmos, the space between you and everything we are going to explore tonight, is less than the distance many people travel to visit family on a weekend. Beyond that 100-kilometer boundary, the Earth's gravity still holds sway for a considerable distance. The Moon, our nearest neighbor in space, the only other world human beings have ever stood on, orbits the Earth at an average distance of approximately 384,000 kilometers. If you drove a car at highway speed without stopping, day and night, maintaining a constant velocity, it would take you approximately 5 months to reach the Moon. The Apollo astronauts, traveling in spacecraft moving far faster than any car, took about 3 days each way. 3 days to reach the nearest object in space. 3 days to reach the only other world our species has ever touched. And yet, here is a fact that tends to rearrange the imagination gently when first encountered. If you took all 7 of the other planets in our solar system, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, and arranged them side by side in a row, they would fit in the space between the Earth and the Moon. All of them, every planet we know, every other world orbiting our Sun, placed side by side in sequence, would fit within the distance to the Moon with room to spare. The Moon, hanging there in the sky, familiar, close enough to see with the naked eye in extraordinary detail, close enough that the light reaching your eye left its surface only a second and a quarter ago, is not even large enough to contain the full breadth of our planetary family arranged in a line. We are already seeing the pattern that will repeat throughout tonight's journey. The distance that seemed large turns out to be small. The scale that seemed vast turns out to be a stepping stone to something vastly more vast. And on, layer by layer, outward into the dark. Chapter 3. The Solar System in True Scale. To understand the true scale of the solar system, it helps enormously to build a model, not a diagram in a textbook where the planets are drawn close together for convenience, their sizes grossly exaggerated relative to the distances between them. A real model, built at a consistent scale, where every distance and every size is proportional to every other. Imagine you are standing in the middle of a large open field on a quiet evening. You place a ball at the center, a ball roughly 1.5 meters in diameter. This ball represents the Sun. At this scale, every other measurement in the solar system follows proportionally. Mercury, the innermost planet, would be a tiny grain approximately 2 millimeters across, smaller than a pea, closer to a small seed. At this scale, Mercury would sit roughly 60 meters from your central Sun. If you place the Sun at one end of a city block, Mercury would be somewhere near the middle of the same block, a 2 millimeter speck on the pavement, almost invisible from a distance. Venus would be slightly larger, about 5 millimeters across, roughly the size of a small peppercorn. Positioned approximately 110 meters from the Sun, Earth would be almost identical in size to Venus at this scale, roughly 5 millimeters in diameter, located about 150 meters away, and the Moon, at this scale, would orbit the Earth at a distance of approximately 40 centimeters, less than half a meter. You could hold your hand out and span the entire Earth-Moon distance at this scale with a comfortable reach. Mars would be a grain about 3 millimeters across, sitting roughly 225 meters from the Sun. Then we cross the asteroid belt and reach Jupiter. Jupiter is the largest planet in the solar system, more than 11 times the diameter of Earth, massive enough that all the other planets combined would fit inside it, with room remaining. In our scale model, Jupiter would be a sphere about 16 centimeters across, roughly the size of a large grapefruit or a small orange, and it would be located approximately 770 meters from our central Sun. 770 meters, nearly a kilometer, just to reach the first of the outer planets. Saturn would be a slightly smaller sphere, about 13 centimeters, roughly the size of a large apple, located just over 1.5 kilometers from the Sun. Its ring system, at this scale, would extend outward another several centimeters in every direction. A thin, flat disk surrounding the sphere, beautiful and precise. Uranus would be a golf ball, roughly 5 centimeters, at approximately 3 kilometers from the center. Neptune, the outermost recognized planet, would be another golf ball at nearly 5 kilometers. Stand back for a moment and take in the full picture this model creates. The Sun is a ball 1.5 meters across at the center of a field. Mercury is a tiny seed 60 meters away. Earth is a small peppercorn 150 meters out. Jupiter is a grapefruit 3/4 of a kilometer away. And Neptune is a golf ball nearly 5 kilometers from the center, further than the distance between two neighborhoods in a mid-sized city. The solar system, in this model, spans a diameter of 10 kilometers. That is a significant distance. That is a walk of an hour or more from one side to the other. And yet, at this scale, the Sun is only 1.5 meters across. The planets are seeds and peppercorns and golf balls, scattered across a 10-kilometer field with enormous distances of empty space between them, because that is the most important thing the model reveals. Not the sizes of the planets, but the distances between them. The solar system is not a crowded place. It is not like the diagrams in textbooks suggest. Planets arranged in neat rows, nearly touching, easy to visit from one to the next. It is almost entirely empty. The planets are tiny specks of matter suspended in an enormous volume of essentially nothing. If you stood on the surface of Earth in this model and tried to see Neptune with the naked eye, you could not do it. Neptune would be a golf ball 5 kilometers away. You would need a telescope of significant power even to find it. The distance between the inner solar system and the outer solar system is, even at this reduced scale, a significant journey. Now consider the light travel times across these distances. Light moves at 300,000 kilometers per second, the fastest speed the universe permits. From the Sun to the Earth, light takes 8 minutes and 20 seconds. From the Sun to Neptune, the outermost planet, light takes just over 4 hours. 4 hours at the speed of light, covering 300,000 kilometers every single second, just to reach the edge of our planetary family. The Voyager, one spacecraft launched in 1977, has been traveling continuously for nearly 5 decades. It is the most distant human-made object ever built, currently more than 23 billion kilometers from Earth. At the scale of our model, where the Sun is a ball 1.5 meters across, Voyager 1 would be located approximately 170 meters beyond Neptune, still within a reasonable walk of the center. And yet, Voyager 1, in reality, is so far from Earth that a radio signal traveling at the speed of light takes more than 20 hours to make the one-way journey between us. We are communicating with it across a distance that light itself needs most of a day to cross. Beyond Neptune, the solar system continues in forms that are less familiar but no less real. The Kuiper Belt, a region of icy bodies, dwarf planets, and ancient frozen debris, extends from roughly 30 to 50 times the Earth-Sun distance. Pluto, reclassified as a dwarf planet in 2006, resides within the Kuiper Belt. The New Horizons spacecraft, which flew past Pluto in 2015, spent 9 years traveling to reach it. And beyond the Kuiper Belt lies the hypothetical Oort cloud, a vast spherical shell of icy bodies thought to surround the solar system at distances ranging from perhaps 2,000 to 100,000 times the Earth-Sun distance. The Oort cloud, if it exists as theorized, is the source of long-period comets, objects that fall inward from the outer reaches of the solar system on journeys that take thousands of years to complete. The outer edge of the Oort cloud, at its theoretical maximum extent, lies approximately 1 to 2 light-years from the Sun, which means our solar system, in its fullest sense, extends roughly halfway to the nearest star. The boundary between our solar system and interstellar space is not a sharp line. It is a gradual fading of the Sun's gravitational influence into the background gravitational field of the galaxy. We are not yet outside the solar system, but we are approaching the edge of everything our Sun can claim. Take a moment with the model we built. The Sun, 1.5 meters across. Neptune, a golf ball 5 kilometers away. The edge of the Oort cloud, somewhere between 40 and 80 kilometers from the center in our scale model. And the nearest star, Proxima Centauri, approximately 40,000 kilometers away. On the other side of the world, the solar system is large, genuinely, measurably, almost incomprehensibly large by human standards. And it occupies a volume of space so small relative to the galaxy it sits within that it is essentially invisible at galactic scales. We have not yet left home, but home is already much larger than it first appeared. Chapter 4. The Nearest Stars. If the solar system already feels large, the distance to the nearest star will require a different kind of patience altogether. Proxima Centauri is the closest star to our Sun. It sits at a distance of approximately 4.24 light-years. That number, 4.24 light-years, is the kind of figure that appears in textbooks and documentaries with such regularity that it can start to feel familiar, manageable even. 4.24. It sounds almost modest. It is not modest. A light-year is the distance that light travels in 1 full year. Light moves at approximately 300,000 kilometers per second. In a single second, light can circle the entire Earth 7.5 times. In 8 minutes and 20 seconds, it travels from the surface of the Sun to the surface of the Earth, 150 million kilometers. In just over 4 hours, it crosses the distance from the Sun to Neptune, the outermost planet. Now, hold that speed in mind and let it run for an entire year. Day after day, night after night, through every season, never stopping, never slowing, covering 300,000 kilometers every single second. At the end of that year, light has traveled approximately 9.5 trillion kilometers. That is 1 light year, a 9 followed by 12 zeros, expressed in kilometers. Proxima Centauri is 4.24 of those. In our earlier scale model, the one where the Sun was a ball 1.5 meters across and Neptune was 5 kilometers away, Proxima Centauri would be located approximately 40,000 kilometers from the center. 40,000 kilometers. That is the circumference of the entire Earth. In a model where Neptune is a short drive away, the nearest star is on the other side of the world. This is what interstellar space actually looks like. Not a crowded neighborhood of nearby suns, but an almost incomprehensible void between isolated points of light. The Voyager 1 spacecraft, launched in 1977, is the most distant human-made object ever created. It is currently traveling at approximately 61,000 kilometers per hour, a speed that seems extraordinary by any human standard. At that velocity, Voyager 1 would reach the distance of Proxima Centauri in approximately 73,000 years. 73,000 years. Modern humans have only existed for roughly 300,000 years. Agriculture was invented about 12,000 years ago. The oldest surviving written language is perhaps 5,000 years old. And our fastest spacecraft, already traveling faster than anything humans have ever built, would need more than 14 times the entire span of recorded human history just to reach the nearest star. That is the silence between stars. And yet, within that silence, there is structure. Proxima Centauri is not alone. It is part of a triple star system, the Alpha Centauri system, which includes two other stars, Alpha Centauri A and Alpha Centauri B, orbiting each other at roughly the distance of Uranus from our Sun, with Proxima Centauri orbiting much further out on a slow, sweeping path that takes hundreds of thousands of years to complete. In the night sky, Alpha Centauri A and B appear as a single bright point to the naked eye, the third brightest star in the sky as seen from Earth. Proxima, being a small red dwarf, is too faint to see without a telescope. And yet, these three stars, neighbors by cosmic standards, are still separated from each other by distances measured in trillions of kilometers. Proxima Centauri has at least one known planet, Proxima b, orbiting within its habitable zone. Whether that planet has an atmosphere, liquid water, or any of the conditions we associate with life, we do not yet know. What we do know is that even if we could send a message to Proxima b at the speed of light, it would take more than 4 years to arrive, and more than 4 years for any reply to return. Ishad conversation would span nearly a decade per exchange. This is what it means to be a civilization on an isolated world. The nearest other star system is so far away that communication alone, at the maximum speed the universe permits, takes years. There are approximately 20 star systems within 13 light years of the Sun. Some of these are single stars, some are binary systems, some are dim red dwarfs that would be invisible to the naked eye, even from much closer distances. Each one is separated from its neighbors by distances measured in light years, trillions of kilometers of mostly empty space. The solar neighborhood, as astronomers sometimes call this region, is a quiet, sparsely populated corner of the galaxy. Stars here are not crowded together. They are separated by enormous distances, each one an island of light in an ocean of dark. And the ocean is very, very large. It is worth pausing here in this chapter to simply sit with that image for a moment, not to rush past it toward the next scale, but to let it breathe. The nearest star to our Sun is so far away that the fastest object humanity has ever launched would need 73,000 years to reach it. There are perhaps 20 stars within a reasonable distance of our own, and each one is separated from the others by years of light travel. Between those stars, there is almost nothing. Thin wisps of interstellar gas, the occasional rogue planet drifting without a sun. cosmic radiation passing through silently, and silence, a silence so complete that it has no earthly equivalent. This is the fabric of the galaxy, not a dense forest of stars, but a vast dark ocean in which stars are separated by distances that dwarf everything we have discussed so far. And the galaxy is much, much larger than its neighborhood. Chapter 5. The Milky Way. Step back further now. Pull your perspective upward and outward until the Sun, Proxima Centauri, and all 20 of the nearest star systems shrink to a single indistinguishable cluster of points, too small and too close together to separate individually. Pull back further still, until that cluster disappears entirely into the larger structure surrounding it. What you would see, from a sufficient distance, is the Milky Way galaxy. The Milky Way is a barred spiral galaxy, a flattened disk of stars, gas, and dust with a bright central bulge, a central bar of stars running through that bulge, and several curved spiral arms extending outward from the bar, like the pattern of cream stirred slowly into coffee. It is not perfectly flat. It has a slight warp toward its outer edges, like a vinyl record left too long in the sun. The diameter of the Milky Way is approximately 100,000 light-years. In some estimates, accounting for the faint outer reaches of the disk, it may be closer to 160,000 or even 200,000 light-years across. 100,000 light-years. We have just spent an entire chapter sitting with the distance to the nearest star, 4.24 light-years, trying to feel the weight of it. The Milky Way is more than 20,000 times wider than that distance. Our Sun sits roughly 26,000 light-years from the galactic center, a little more than halfway out from the core toward the edge, in a relatively quiet region between two of the spiral arms. We are not at the center. We are not at the edge. We are somewhere in the middle, in an unremarkable suburb of a vast cosmic city. The galactic center is a region of extraordinary density and activity. Stars there are packed far more tightly than in our neighborhood. At the very center sits a supermassive black hole, Sagittarius A star, with a mass approximately 4 million times that of our Sun. If you stood on a planet near the galactic center, the night sky would be blazing with nearby stars, many of them close enough to cast faint shadows. It would look nothing like the night sky we know. From our position, 26,000 light-years out, the galactic center is invisible to the naked eye. Hidden behind vast clouds of gas and dust that block visible light. We can detect it in radio waves and infrared, but not with our eyes alone. In a sense, we live on a planet from which our own galaxy's heart is hidden. The Milky Way contains somewhere between 100 billion and 400 billion stars. The range of that estimate reflects genuine uncertainty. Counting stars in a galaxy you are embedded inside is an extraordinarily difficult task. Each of those stars is, on average, separated from its neighbors by distances similar to the ones we explored in the previous chapter. The galaxy is not a solid object. It is an enormous, mostly empty structure in which stars are scattered like grains of sand across a surface the size of a continent. Light takes 100,000 years to cross it. To appreciate what that means, consider this. When the light now reaching the far edge of the Milky Way from our Sun first left the Sun, human beings did not yet exist. Homo sapiens emerged as a species roughly 300,000 years ago. The light that left our Sun 100,000 years ago, light that is only now, in this moment, reaching the far edge of our own galaxy, departed when our ancestors were living in small groups, using stone tools, in a world that had no written language, no agriculture, no permanent settlements of any kind. Our galaxy is so large that light leaving it from one side has been traveling since before modern humans existed by the time it reaches the other. The Milky Way takes approximately 225 million years to complete one full rotation. One galactic year. In that time, the Sun and all the planets orbiting it travelled together around the galactic centre at a speed of roughly 828,000 kilometers per hour. Despite that extraordinary speed, the journey is so vast that it still takes 225 million years. The Earth is approximately 4.5 billion years old. That means our planet has completed roughly 20 orbits of the galactic centre since its formation. 20 galactic years. In the first of those galactic years, life on Earth had not yet appeared. By the fifth or sixth, the first complex single-celled organisms were beginning to emerge. Multicellular life did not arrive until roughly the 15th galactic year. Dinosaurs appeared and disappeared in the span of less than one galactic year. Human civilization occupies a tiny fraction of a single galactic orbit. The Milky Way is not just large in space, it is large in time. It operates on timescales that make human history feel like a momentary flicker. And the Milky Way is just one galaxy. There are galaxies far smaller than ours. Dwarf galaxies containing only a few 100 million stars, orbiting the Milky Way like satellites orbit a planet. The large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere as faint smudges of light, are two such dwarf galaxies. The large Magellanic Cloud is approximately 160,000 light-years away. The small Magellanic Cloud is about 200,000 light-years distant. Both are close enough to interact gravitationally with the Milky Way. Both are slowly being drawn in by our galaxy's gravity, their stars and gas gradually being incorporated into the larger structure over billions of years. The universe, even at the scale of galaxies, is not a static place. It is always moving, always pulling, always changing on timescales too vast for human experience to register. Chapter 6. What Webb changed for most of human history? Our understanding of the universe beyond the Milky Way was limited by what our instruments could detect. The first telescopes, built in the early 17th century, revealed mountains on the Moon, moons orbiting Jupiter, and the individual stars of the Milky Way. They were revolutionary instruments that transformed our understanding of the solar system. But the universe beyond our galaxy remained largely invisible and largely unconsidered. For a long time, astronomers debated whether the faint fuzzy patches of light visible through telescopes, called nebulae, were clouds of gas within the Milky Way, or whether they were separate, distant galaxies in their own right. The question was not resolved until the 1920s, when Edwin Hubble used the newly completed Hooker telescope on Mount Wilson to measure the distance to the Andromeda Nebula and determined that it was far too distant to be part of the Milky Way. It was, instead, a separate galaxy, what he called an island universe, containing billions of stars of its own. That discovery fundamentally changed our understanding of the cosmos. The Milky Way was not the universe. It was one galaxy among many. But how many? And how far did they extend? Over the following decades, telescopes improved. Photographic techniques became more sensitive. Radio astronomy opened up entirely new wavelengths of observation. Gradually, the picture of a vast universe filled with galaxies began to come into focus. Then, in 1990, the Hubble Space Telescope was launched, the first large optical telescope placed in orbit above Earth's atmosphere. free from the blurring effects of air, Hubble could see with a clarity and depth that no ground-based telescope could match. In 1995, astronomers pointed Hubble at a small, apparently empty patch of sky, an area roughly 1/24 millionth of the total sky, chosen specifically because it appeared to contain nothing of interest. They kept the telescope pointed there for 10 consecutive days, collecting every photon that arrived. What emerged from that exposure was the Hubble Deep Field image, one of the most significant photographs in the history of science. In that tiny patch of apparently empty sky, Hubble found approximately 3,000 galaxies, each one a separate island universe containing billions of stars at distances ranging from hundreds of millions to billions of light years away. The universe was not empty between the galaxies. It was full of galaxies. Subsequent deep field images, the Hubble Ultra Deep Field in 2004 and the Hubble Extreme Deep Field in 2012, pushed even further. The Extreme Deep Field image, covering an area of sky smaller than a millionth of the full sky, revealed approximately 5,500 galaxies, some of them so distant that the light reaching Hubble had been traveling for more than 13 billion years. These were some of the earliest galaxies ever observed, structures that formed when the universe was only a few 100 million years old. And then came the James Webb Space Telescope. Webb was launched on Christmas Day, 2021, after decades of development and construction. It is the largest and most complex space telescope ever built. Its primary mirror, made up of 18 hexagonal gold-coated segments, spans 6.5 meters across. It observes primarily in infrared light, which allows it to see through dust clouds that block visible light and to detect the highly redshifted light of the most distant galaxies in the universe. In July of 2022, the first full-color science images from Webb were released to the public. One of them, Webb's first deep field, showed thousands of galaxies in a patch of sky roughly the size of a grain of sand held at arm's length. Some of those galaxies had never been seen before. Some of them showed structures forming in the universe's first few 100 million years. Some of them were gravitationally distorted by the mass of galaxy clusters between them and us. Their light bent and stretched into arcs by a phenomenon predicted by Einstein's general theory of relativity. Webb did not just see further than Hubble. It saw more clearly. It saw in greater detail. It revealed galaxies that had previously been invisible, not because they weren't there, but because our instruments weren't sensitive enough to detect them. What Webb showed us in those first images was a universe of almost incomprehensible density and age, a universe in which every direction we look, at every distance we can measure, there are galaxies, hundreds of billions of them, each one containing hundreds of billions of stars, each one separated from its neighbors by millions of light years of space. Webb changed the scale of what we thought we could see, and in doing so, it changed the scale of what we understand the universe to be. We are still processing what it revealed. The data coming from Webb continues to be analyzed, continues to challenge existing models, continues to push the boundaries of what we thought we knew about the early universe and the formation of its first structures. What it has confirmed, beyond any doubt, is that the universe is incomprehensibly larger and older and richer than anything our unaided eyes could ever suggest, and we are only beginning to understand it. Chapter 7. The Local Group. Pull back further now, further than the Milky Way, further than the Magellanic Clouds, further than the individual galaxies we can name and study and point to in the sky. Pull back until the Milky Way itself, that vast disk of 100 billion stars, 100,000 light-years across, shrinks to a single faint smudge among other faint smudges. What you would see from that distance is the local group. The local group is the name astronomers give to the small cluster of galaxies to which the Milky Way belongs. It is our galactic neighborhood, the collection of galaxies bound together by mutual gravity, moving together through space, interacting with each other across millions of years of cosmic time. The local group contains more than 50 known galaxies. Most of them are small, dwarf galaxies containing only a few 100 million stars, orbiting the two dominant members of the group, the way moons orbit planets. The two dominant members are the Milky Way and the Andromeda galaxy. Andromeda, also known by its catalogue designation M31, is the largest galaxy in the local group. It is a spiral galaxy, broadly similar in structure to the Milky Way, though somewhat larger, containing perhaps 1 trillion stars compared to the Milky Way's estimated 100 to 400 billion. It is visible to the naked eye on a clear, dark night as a faint, elongated smudge in the constellation Andromeda, the most distant object a human being can see without any optical aid. The light reaching your eyes when you look at Andromeda left that galaxy approximately 2.5 million years ago. 2.5 million years. When that light began its journey toward us, our ancestors were not yet fully human. Homo sapiens did not exist. The creatures whose descendants would eventually build telescopes and study the cosmos were small, upright walking primates living on the African savanna, with no language, no tools beyond, simple stones, no concept of the stars they slept beneath each night. That light has been traveling through space ever since, through the rise and fall of every human civilization, through every war and discovery and forgetting. And it arrives at your eye tonight, if you go outside and look in the right direction, as a faint, soft smudge of ancient light. Andromeda is approximately 2.5 million light-years from the Milky Way. In the context of everything we have discussed so far, that might seem like an enormous distance. And it is. But within the local group, Andromeda and the Milky Way are, in a meaningful sense, close neighbors. They are gravitationally bound to each other. They are, in fact, approaching each other. Andromeda is moving toward the Milky Way at approximately 110 kilometers per second. In approximately 4.5 billion years, roughly the current age of the Earth, the two galaxies will collide. Galaxy collisions are not the violent, catastrophic events the word collision might suggest. Galaxies are mostly empty space, and when two of them merge, individual stars almost never actually strike each other. The distances between stars are simply too vast. Instead, the two galaxies will pass through each other, their gravitational fields distorting and reshaping each other's structure, pulling stars into new orbits, triggering enormous bursts of star formation as gas clouds are compressed by the interaction. The process will take billions of years. Over multiple passes and interactions, the two galaxies will gradually merge into a single larger elliptical galaxy, sometimes informally called Milkomeda or Milkdromeda. The Sun and Earth, if they still exist at that point, will likely be flung into a new orbit within the merged galaxy, far from their current position. It is a reminder that nothing in the universe is permanent, not even galaxies. The local group extends across an area roughly 10 million light-years in diameter. 10 million light-years to contain 50-odd galaxies, most of them small, 2 of them large, all of them bound together by gravity into a single gravitational system, moving through the larger universe. Beyond the local group, the density of galaxies does not decrease. It simply reorganizes into larger and larger structures, clusters, superclusters, filaments, all the way up to the largest structures in the observable universe. But within the local group, there is a certain intimacy. These are our galaxies, the ones whose light we can see with our naked eyes on the right night, the ones whose gravitational influence will eventually reshape our own galaxy, the ones that, in some distant cosmic sense, we share a neighborhood with. It is worth taking a moment to feel the scale of that neighborhood. 10 million light years. Light traveling for 10 million years to cross from one side to the other. And yet, within the larger structure of the universe, the local group is a small, quiet, relatively isolated corner. The universe has much larger structures in store. Chapter 8. The Cosmic Web. There is a structure to the universe that only becomes visible when you step back far enough to see it. Not the scale of a solar system, or a galaxy, or even a galaxy cluster. Something larger. Something that only resolves into clarity when you pull your perspective back to distances of hundreds of millions of light years. When individual galaxies shrink to points of light, and the space between them begins to reveal a pattern. The pattern is called the Cosmic Web. It is one of the most remarkable discoveries in the history of cosmology. When astronomers began mapping the distribution of galaxies across large volumes of space in the latter decades of the 20th century, they expected to find galaxies distributed more or less randomly, scattered throughout space like raisins in a bread, with perhaps some clustering but no grand organizing structure. What they found instead was something they had not anticipated. Galaxies are not randomly distributed. They are arranged in an intricate, three-dimensional web of filaments, walls, and nodes, separated by enormous empty regions called voids. The filaments are long, thread-like structures, rivers of galaxies and galaxy clusters stretching across hundreds of millions of light years, connected at their intersections to dense knots called nodes or superclusters. The walls are flat, sheet-like arrangements of galaxies spanning similar distances, and between the filaments and walls lie the voids, vast, nearly empty regions of space that can span hundreds of millions of light years in diameter, containing almost no galaxies at all. The overall impression, when visualized in 3 dimensions, is strikingly similar to certain natural structures found at far smaller scales. It resembles the structure of a sponge. It resembles the network of neurons in a brain. It resembles the structure of foam. Billions of soap bubbles pressed together, with matter concentrated along the boundaries, between bubbles and almost nothing in their interiors. This similarity is not coincidental in the sense of being random. It reflects something deep about the physics of how structure forms under gravity. The same mathematical principles that govern how matter clusters operate across an enormous range of scales. But the resemblance to biological structures is nonetheless striking enough to give pause. The largest structures in the cosmic web have names. The Laniakea supercluster, identified and named in 2014, is the supercluster within which the Milky Way resides. Laniakea, a Hawaiian word meaning immeasurable heaven, spans approximately 500 million light years and contains the mass of approximately 100 million billion suns. It includes the local group, the Virgo cluster, a dense concentration of more than 1,000 galaxies about 53 million light-years from the Milky Way, and hundreds of other galaxy groups and clusters, all of them slowly flowing toward a gravitational center called the Great Attractor. The Great Attractor is a region of gravitational anomaly located roughly 250 million light-years from the Milky Way, in the direction of the constellation Centaurus. It is a point toward which an enormous volume of space, including our own galaxy, is being pulled at hundreds of kilometers per second. For a long time, the Great Attractor was difficult to study because it lies almost exactly behind the dense plane of the Milky Way's own disk, hidden behind the dust and stars of our own galaxy. Modern infrared and radio observations have since pierced through that obscuring layer and identified a massive concentration of galaxy clusters at the Great Attractor's location, most prominently the Norma cluster, a dense aggregation of hundreds of galaxies. But even the Norma cluster may itself be falling toward an even larger structure. The Shapley supercluster, one of the most massive concentrations of matter in the observable universe, located roughly 650 million light-years away. The cosmic web, in other words, has a hierarchy. Galaxies cluster into groups. Groups cluster into clusters. Clusters connect along filaments into superclusters. Superclusters flow towards still larger attractors. And all of this, every galaxy, every cluster, every filament and void, is embedded within the largest structure of all, the observable universe itself. The voids between the filaments deserve their own moment of consideration. The Boötes void is one of the largest known voids in the observable universe. It is a roughly spherical region of space approximately 330 million light-years in diameter, located about 700 million light-years from Earth. Within this enormous volume, a sphere 330 million light-years across, there are only a handful of known galaxies, a region of space that, if it were filled with galaxies at the average density of the universe, would contain thousands of them, contains almost nothing. 330 million light-years of almost nothing. The Boötes void is not unique. Voids like it exist throughout the cosmic web, enormous empty bubbles that make up the majority of the universe's volume. Most of the universe, by volume, is void. The matter, the galaxies, the stars, the gas, is concentrated into the thin boundaries between these vast empty regions, like the surface of soap bubbles in foam. We live in a universe that is, in the most literal sense, mostly empty, not just at the scale of atoms, where electrons orbit nuclei across enormous relative distances, not just at the scale of solar systems, where planets are separated by billions of kilometers of vacuum, but at the grandest scale of all, the scale of the universe itself. Matter is a thin, delicate web stretched across an ocean of nothing. The cosmic web is the largest structure that exists. Beyond it, there is no larger organizational pattern. Only the universe as a whole, expanding in every direction, carrying the web within it like a pattern printed on the surface of an inflating balloon. And that balloon, that expanding universe, is what we turn to next. Chapter 9. The Observable Universe. We have traveled a long way tonight, from the familiar scale of a human body, outward through the solar system, past the nearest stars, across the breadth of the Milky Way, through the local group, and into the vast filaments and voids of the cosmic web. Each step outward has required a new calibration of scale, a new willingness to let go of previously held intuitions and accept a larger frame of reference. Now, we arrive at the larger scale we can directly observe. the observable universe itself. The observable universe is not the same as the universe. It is the portion of the universe from which light has had enough time to reach us since the beginning of cosmic time. Because the universe is approximately 13.8 billion years old, and because light travels at a finite speed, there is a limit to how far we can see, a horizon beyond which no information has yet had time to arrive. You might expect, given a universe 13.8 billion years old, that the observable universe would extend 13.8 billion light-years in every direction. But it does not. The observable universe extends approximately 46.5 billion light-years in every direction, giving it a total diameter of roughly 93 billion light-years. The reason for this apparent discrepancy is the expansion of space itself. The universe has been expanding since the Big Bang. The galaxies we observe at the edge of the observable universe emitted their light when the universe was very young, when those galaxies were much closer to us than they are now. In the time that light has been traveling toward us, space itself has expanded, carrying those galaxies much further away. The light was emitted from a position relatively close to us, but the source of that light is now, due to expansion, tens of billions of light-years further away than the distance the light has actually traveled. This is one of the most conceptually difficult aspects of modern cosmology to absorb. Space is not a fixed stage on which galaxies move. Space itself is a dynamic medium that stretches and expands. The galaxies are not, for the most part, flying apart through space under their own power. They are being carried apart by the expansion of the space between them. The distinction matters enormously for understanding the true size of the observable universe. The observable universe contains an estimated 2 trillion galaxies, a figure revised upward significantly from earlier estimates of 200 billion, based on deeper surveys enabled by telescopes like Hubble and Webb. 2 trillion galaxies, each containing hundreds of billions of stars, spread across a volume 93 billion light-years in diameter. 2 trillion is a number that resists intuitive understanding. If you tried to count to 2 trillion at the rate of 1 number per second, it would take you approximately 63,000 years. If each galaxy were represented by a single grain of sand, the total volume of sand would fill a space larger than the Earth. And each of those grains of sand is itself a galaxy, an island universe containing hundreds of billions of suns, many of them orbited by planets, some of those planets perhaps harboring conditions suitable for life of some kind. The numbers are not merely large. They are large in a way that exceeds the capacity of human intuition entirely. We can write them down. We can manipulate them mathematically. But we cannot feel them the way we feel the distance across a room or the weight of an object in our hand. This is not a failure of imagination. It is simply the honest acknowledgement that the universe did not build itself to fit within the limits of a primate's perceptual system. The scales involved are what they are, regardless of whether we can intuitively grasp them. The cosmic microwave background radiation, the faint afterglow of the Big Bang itself, marks the practical limit of what we can observe. It is the light emitted approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely for the first time. Before that moment, the universe was a hot, opaque plasma through which light could not pass. The cosmic microwave background is therefore the oldest light we can ever observe. A wall of ancient radiation surrounding us in every direction, the surface of last scattering, beyond which our view is forever blocked. The James Webb Space Telescope has pushed our observations closer to that wall than ever before. Its infrared sensitivity allows it to detect galaxies forming in the universe's first few 100 million years, structures so distant and so ancient that their light has been traveling toward us for more than 13 billion years. When Webb observes these early galaxies, it is not just seeing far away, it is seeing far back in time. Distance and time are inseparable in cosmology. To look outward is to look backward. The further away an object is, the younger the universe was when its light began the journey to us. At the very edge of the observable universe, we see the universe as it was nearly 14 billion years ago. We see the conditions from which everything, every galaxy, every star, every planet, every living thing, eventually emerged. We are looking at our own origins, and what lies beyond that horizon, beyond the cosmic microwave background, beyond the edge of what we can see, is a question we will explore in the next chapter. For now, let the observable universe settle around you. 93 billion light-years in diameter, 2 trillion galaxies, the largest structure we can directly observe, and yet, almost certainly, a small fraction of the universe as a whole. You are somewhere near the middle of all of this, on a planet, around a star, in a galaxy, in a cluster, in a supercluster, in a web, in a universe. Take a slow breath. Let that settle. Chapter 10. What lies beyond? There is a question that arises naturally at this point in our journey, and it is one of the most profound questions in all of cosmology. If the observable universe extends 46.5 billion light-years in every direction, if that is the limit of what we can see, the boundary beyond which no light has yet had time to reach us, what lies beyond it? The honest answer is that we do not know. Not with certainty, not with the kind of direct observational evidence that science prefers. What lies beyond the observable universe is, by definition, beyond our ability to observe. No telescope we build, no matter how sensitive, no matter how large, will ever be able to see beyond the cosmic horizon. The limit is not technological, it is fundamental. It is written into the physics of light and time and the age of the universe itself. But we are not entirely without tools for thinking about it. The observable universe is not the universe. It is the portion of the universe visible to us from our particular location in space at this particular moment in cosmic time. An observer in a galaxy 10 billion light-years away would have their own observable universe, a sphere of the same radius, centered on their location, overlapping with ours, but extending into regions we will never see. Every point in space has its own observable universe, its own horizon, its own bubble of accessible information. The question is, what fills the space beyond all those horizons? The space that no observer can currently see. The most straightforward assumption, and the one that most cosmologists consider most likely given what we know about the universe, is that the universe continues beyond the observable horizon in roughly the same way it exists within it. More galaxies, more galaxy clusters, more filaments and voids in the cosmic web, more of the same large-scale structure we observe around us, extending far beyond the limits of our vision. How much further? Current models of cosmic inflation, the period of extraordinarily rapid expansion thought to have occurred in the universe's first tiny fraction of a second, suggest that the total universe could be vastly larger than the observable portion. Some models suggest the total universe is at least 100 times larger than what we can see. Others suggest it could be thousands of times larger. Some versions of inflationary theory suggest the total universe could be effectively infinite, extending without boundary or edge in every direction. An infinite universe is a genuinely difficult concept to hold, not because the mathematics is unclear. Mathematicians have worked with infinite sets for centuries, but because the physical implications are deeply strange. In an infinite universe, every possible arrangement of matter would exist somewhere. Every possible history, every possible configuration of particles and fields and forces, repeated infinitely many times, distributed throughout an infinite volume of space. This is one of the ideas that emerges from serious cosmological thinking, and that the human mind tends to push away, not because it is wrong, but because it is too large to comfortably contain. There is another possibility, less intuitive but not ruled out by current data. The universe could be finite but without a boundary, curved back on itself in a higher dimension, the way the surface of a sphere is finite but has no edge. If you traveled in one direction long enough in such a universe, you would eventually return to where you started. The universe would be closed, finite, and yet boundless. No wall, no edge, just a curvature so gentle that it is undetectable at the scales we can observe. Current measurements of the universe's geometry suggest that it is very close to flat, the kind of geometry in which parallel lines never meet, and the angles of a triangle always add up to 180 degrees. If the universe is perfectly flat, it is either infinite or so large that the curvature is unmeasurably small. Either way, it extends far, far beyond what we can see. Beyond the observable universe, there may also be regions of space that expanded faster than our own during the inflationary period. Regions that are now receding from us faster than light, forever beyond our reach, forever beyond our knowledge. These regions are not violating the cosmic speed limit. Nothing within them is moving through space faster than light. It is space itself that is expanding between us and them faster than light can cross it. The result is the same: permanent, fundamental separation. And then there are the more speculative ideas, the multiverse hypotheses that emerge from various branches of physics and cosmology. The many worlds interpretation of quantum mechanics suggests that every quantum event spawns branching parallel universes. String theory's landscape suggests an almost incomprehensible number of possible universes, each with different physical constants and laws. Eternal inflation suggests that our Big Bang was one of many, that bubble universes form continuously within a larger inflationary background, each one a separate cosmos with its own history. These ideas are not science fiction. They emerge from serious attempts to extend our best physical theories beyond the boundaries of what we can observe. Whether any of them are correct is a question that may never be definitively answered, precisely because the regions they describe are beyond observation. What we can say with confidence is this: the observable universe, vast as it is, containing 2 trillion galaxies across 93 billion light-years, is almost certainly not the whole of what exists. It is our window, our portion, the slice of reality that the laws of physics and the age of the universe have made accessible to us. Beyond that window, the universe continues. In what form? To what extent? Governed by what principles? These are questions that sit at the edge of human knowledge, looking out into a darkness that may never be fully illuminated. There is something quietly wonderful about that. Not frightening, not distressing, simply honest. The universe is larger than we can know, and we know that it is larger than we can know. That is itself a remarkable thing to understand. Let that sit for a moment before we continue. We have now traveled from the scale of a human body to the very edge of the observable universe and beyond, to the unknown territory that lies past our cosmic horizon. In the chapters that remain, we will turn our attention to a different kind of question. Not how large the universe is, but how we came to know how large it is. How human beings, standing on a small planet around an ordinary star, manage to measure distances that make the imagination stagger. Chapter 11. How we measure the unmeasurable. It is one thing to say the universe is 93 billion light-years in diameter. It is another thing entirely to explain how we know that. The measurement of cosmic distances is one of the greatest achievements in the history of human knowledge. It required centuries of careful observation, the development of entirely new branches of mathematics and physics, and a series of ingenious techniques, each one building on the last, extending our reach further and further into the cosmos. Astronomers call this sequence of techniques the cosmic distance ladder. Each rung of the ladder uses a different method, valid over a different range of distances, with each method calibrated against the one below it. Together, they form an unbroken chain of measurement, stretching from our own solar system to the edge of the observable universe. The first rung of the ladder is the most direct. It is called parallax, and it works in exactly the same way that your brain uses the slightly different views from your two eyes to perceive depth. Hold a finger up in front of your face and close one eye. Now open that eye and close the other. Your finger appears to jump against the background. The closer your finger is, the larger the jump. This apparent shift in position depending on the viewing angle is parallax, and your brain uses it unconsciously to judge distances in the world around you. Astronomers use the same principle, but instead of two eyes separated by a few centimeters, they use two positions of the Earth in its orbit around the Sun, separated by 300 million kilometers, the diameter of Earth's orbit. By photographing a nearby star in January and again in July, and measuring the tiny apparent shift in the star's position against the background of much more distant stars, astronomers can calculate the star's distance using simple geometry. This technique works for stars within a few thousand light-years of the Sun. Beyond that distance, the parallax shift becomes too small to measure reliably, even with the most sensitive instruments available. The European Space Agency's Gaia mission, which has been mapping stellar positions with extraordinary precision since 2013, has extended the reach of parallax measurements to several thousand light-years. But beyond that, a different technique is needed. The second rung of the ladder uses a remarkable class of stars called Cepheid variables. These are stars that pulsate, expanding and contracting in a regular rhythm, brightening and dimming as they do so. The period of this pulsation, the time between successive brightness peaks, is directly related to the star's intrinsic luminosity, how much light it actually produces. This relationship was discovered by the American astronomer Henrietta Swan Leavitt in 1908, while she was working at the Harvard College Observatory. By studying Cepheid variables in the small Magellanic Cloud, a nearby dwarf galaxy, Leavitt noticed that the brighter Cepheids had longer periods. Since all the stars in the small Magellanic Cloud were at roughly the same distance from Earth, differences in their apparent brightness reflected real differences in their intrinsic luminosity. Leavitt had found a way to determine how much light a Cepheid actually produces, simply by timing its pulsation. Once you know a star's intrinsic luminosity, you can calculate its distance by comparing that luminosity to how bright it appears in the sky. A star that is intrinsically very bright but appears faint must be very far away. The mathematics is straightforward, following an inverse square law. Brightness falls off with the square of the distance. Leavitt's discovery was transformative. It gave astronomers a standard candle, an object of known intrinsic brightness that could be used to measure distances far beyond the reach of parallax. Edwin Hubble used Cepheid variables to measure the distance to the Andromeda galaxy in the 1920s, establishing definitively that it lay far beyond the boundaries of the Milky Way. Cepheid variables can be detected in galaxies tens of millions of light-years away, but beyond that distance, even the Hubble Space Telescope struggles to resolve individual stars. A third rung of the ladder is needed. That rung is provided by a particular type of stellar explosion, called a Type 1a supernova. These explosions occur in binary star systems where a white dwarf, the dense remnant of a dead star, gradually accumulates material from a companion star until it reaches a critical mass and ignites in a thermonuclear explosion. Because the critical mass at which the explosion occurs is always the same, the peak brightness of a Type 1a supernova is always roughly the same. They are, like Cepheids, standard candles, but far brighter ones, visible across billions of light-years. By observing Type 1a supernovae in distant galaxies and comparing their apparent brightness to their known intrinsic brightness, astronomers can measure distances across the full observable universe. It was observations of distant Type 1, a supernovae, in the late 1990s that led to the discovery of dark energy, the mysterious force driving the accelerating expansion of the universe. One of the most significant cosmological discoveries in decades. Beyond even supernovae, cosmologists use the large-scale structure of the cosmic microwave background, the detailed pattern of temperature fluctuations in the oldest light in the universe, as a ruler of cosmic dimensions. The physical size of the fluctuations in that pattern is known from first principles of physics, and by comparing that known size to the angular size observed in the sky, astronomers can calculate the distance to the surface of last scattering and constrain the overall geometry and size of the observable universe. Each rung of the cosmic distance ladder rests on the one below it. Parallax calibrates Cepheids. Cepheids calibrate supernovae. Supernovae and the cosmic microwave background together constrain the large-scale structure of the universe. Uncertainties at each rung propagate upward through the chain, which is why cosmologists work so carefully to reduce errors at every stage. The entire edifice of our knowledge of cosmic distances, everything we have discussed tonight about light years and galaxy clusters and the size of the observable universe, rests on this ladder, on centuries of patient observation, on the insight of scientists like Leavitt, whose foundational discovery went largely uncelebrated during her lifetime, on the careful accumulation of measurements, each one extending our reach a little further into the dark. There is something deeply human about this process. We are small creatures on a small planet, using the most delicate instruments our civilization can build, measuring the distances to objects so remote that the light reaching us left them before our species existed, and we are doing it successfully, imperfectly, with uncertainties and ongoing debates about the precise values of certain key measurements, but successfully, in the broad sense that our measurements are consistent, cross-validated, and grounded in well-tested physics. We are a species that learned to measure the universe it lives in. That is not a small thing. Chapter 12. What scale does to the mind? There is a particular feeling that tends to arise when we contemplate the scales we have been exploring tonight. It is difficult to name precisely. It is not quite fear, though it has some of fear's qualities. A certain loss of footing, a sense of the familiar becoming unfamiliar. It is not quite wonder, though wonder is certainly part of it. It is something in between. A feeling of the self becoming temporarily small in a way that is both uncomfortable and, in a quieter moment, deeply clarifying. The philosopher and scientist Carl Sagan called it a sense of the numinous, an awareness of something vast and ancient and indifferent to human concerns, not hostile, not benevolent, simply immeasurably larger than anything we are accustomed to thinking about. He believed this feeling, properly understood, was not a cause for despair, but for a particular kind of grounded wonder. The universe does not need us to be meaningful for our lives to have meaning. The two things are separate. Psychologists who study the emotion of awe, a close relative of what we are describing, have found that it tends to produce a distinctive cognitive effect. When people experience genuine awe, their sense of self temporarily diminishes. The boundaries of the ego become less sharp. The concerns and preoccupations that normally occupy the foreground of consciousness recede. In their place arises a kind of openness, an expanded awareness that something larger than the self exists. Research suggests that this experience has measurable effects on well-being. People who regularly experience awe tend to report higher levels of life satisfaction, greater feelings of connection to others, and a reduced tendency towards self-preoccupation. The temporary loss of self that awe produces seems, paradoxically, to leave people feeling more connected rather than less. This may explain why so many people, across so many cultures, and throughout so much of human history, have found comfort and meaning in contemplating the night sky. Not because the sky provides answers to human questions. It does not. The stars are indifferent to our questions. But the act of looking, truly looking, with some understanding of what is actually out there, seems to do something beneficial to the human mind. It loosens something. It puts things in perspective in a way that is difficult to achieve by any other means. There is also a more specific cognitive challenge that cosmic scale presents, and it is worth acknowledging honestly. The human brain did not evolve to understand distances of billions of light years. It evolved to navigate a world of meters and kilometers, to judge the distance of a predator, to estimate the time it would take to reach a water source, to plan a journey of perhaps a few hundred kilometers at most. The neural machinery we use to process spatial information was built for a world many orders of magnitude smaller than the cosmos. When we encounter cosmic distances, our spatial intuition simply fails. We can hold the numbers intellectually, we can manipulate them mathematically, but we cannot feel them the way we feel the distance across a room. The brain has no perceptual template for a light year, let alone a billion light years. This is not something to be embarrassed about. It is simply the honest description of a limitation that every human being shares, including every astronomer and cosmologist who has ever lived. Understanding cosmic scale is a matter of careful reasoning and calibrated imagination, not of raw perceptual experience. What we can do, what seems to help, both practically and emotionally, is to approach these scales through analogy and comparison, not because the analogies are perfect, but because they give the mind something to hold while the larger numbers are being contemplated. A basketball for the Earth, a grain of sand for a planet. The entire human history of walking to circle the globe a handful of times, These are scaffolding, temporary supports that make the climb possible even when the top is out of sight. And there is something else worth noting. The very fact that we find cosmic scale difficult to grasp is itself meaningful. It tells us something about the kind of beings we are, creatures whose evolved perceptions are finely tuned to a particular range of scales, a narrow window in the vast spectrum of sizes the universe contains. We are not universal observers. We are particular observers with particular limitations, trying to understand something that vastly exceeds our intuitive reach. That effort, the reaching, is perhaps the most distinctly human thing there is. Philosophers have long noted that the encounter with vastness tends to produce one of two broad responses. The first is what might be called the despair of insignificance, the feeling that because the universe is so large and human life so brief and small, nothing we do or feel or create truly matters. This response, while understandable, rests on a confusion. It assumes that meaning is something the universe must supply from the outside, and that size is the measure of importance. Neither of these assumptions holds up under examination. The second response is quieter but more sustaining. It is the recognition that consciousness, the capacity to observe and reflect and feel and understand, is itself remarkable, regardless of the scale at which it operates. A universe without observers would have no one to note its vastness. The fact that matter, organized in a particular way on a particular planet, has become capable of measuring the distance to galaxies billions of light years away. That is not a small thing. That is, in fact, extraordinary. You are part of that. Your awareness of the scales we have discussed tonight is itself a part of the universe becoming aware of itself. The same atoms that were forged in stellar interiors and scattered across space by supernova explosions are, right now, arranged inside your skull in a configuration that is contemplating the universe from which they came. There is no scale at which that becomes insignificant. Chapter 13. Earth in Perspective. We have travelled a long way tonight, from the scale of a human body to the edge of the observable universe, from the familiar weight of a footstep to the incomprehensible distances between galaxy clusters, from the thin blue line of Earth's atmosphere to the cosmic web of filaments stretching across hundreds of millions of light-years of space. Now we return, not because the outward journey is over, it never really ends, but because there is value in coming back, in taking everything we have encountered on this long, slow journey outward and bringing it home, in looking at the small, familiar world we started from and seeing it differently than we did when we left. The Earth, from space, is a sphere approximately 12,700 kilometers in diameter. It is mostly ocean. About 71% of its surface is covered by water, giving it a blue appearance when seen from a sufficient distance. It has a single large moon and an atmosphere thin enough to cross in an hour of vertical travel, and a surface temperature range that permits liquid water to exist across much of its area for much of its history. These are the facts, but facts, by themselves, do not convey the particular quality of what the Earth looks like when seen from far away. In 1990, the Voyager 1 spacecraft was approximately 6 billion kilometers from Earth, beyond the orbit of Neptune, near the edge of the planetary solar system. When mission controllers turned its camera back toward the inner solar system for one final set of photographs before the camera was permanently switched off to conserve power for other instruments. In the resulting image, the Earth appears as a pale blue dot, a tiny point of light, less than a single pixel across, suspended in a beam of scattered sunlight against the absolute blackness of space. It is almost invisible. It is easy to miss entirely if you don't know where to look. Carl Sagan, who had advocated for taking the photograph, described it this way. He wrote that the image underscored our responsibility to deal more kindly with one another and to preserve and cherish that pale blue dot, the only home we have ever known. The photograph was taken from a distance of 6 billion kilometers. Voyager 1 is now more than 23 billion kilometers from Earth and still traveling outward at 61,000 kilometers per hour. And 6 billion kilometers, the distance from which our entire world appears as a single pixel, is itself an almost negligible distance compared to the scales we have been exploring tonight. It is less than one light day. It is a small fraction of the distance to even the nearest star. From the distance of Proxima Centauri, the Earth would not be visible at all, not even with the most sensitive telescope currently in existence. Our planet, our oceans and continents and cities, and everything that has ever happened on its surface would be hidden in the glare of the sun, a pale star, one among hundreds of billions, in the outer arm of an ordinary spiral galaxy. From the distance of the Andromeda galaxy, the entire Milky Way would appear as a faint smudge of light. The sun would be invisible. The Earth would be invisible. The entire history of life on this planet, every organism that has ever lived, every thought that has ever been thought, every word that has ever been spoken, would be contained within a structure too small to resolve in even the most powerful telescope. From the edge of the observable universe, the Milky Way itself would be invisible. Our entire galaxy, with all its hundreds of billions of stars, would fall below the threshold of detection at such a distance. The local group, our entire cluster of galaxies, spanning 10 million light-years, might, under ideal conditions, be detectable as a single faint point of light among the billions of other points scattered across the deep field. And the Earth, this planet, this world, this place where you are lying or sitting right now, breathing slowly, perhaps drifting towards sleep, the Earth would be nothing at all, not even a concept, not even an abstraction, simply absent, indistinguishably folded into the fabric of the larger universe. This is the honest perspective that cosmic scale provides. Not a comfortable one, perhaps, but an honest one. And yet here we are, on that invisible world, around that invisible star, in that ordinary galaxy. And we know all of this. We have measured it. We have reasoned our way to it across centuries of careful observation and thought. We have built instruments delicate enough to detect the light of galaxies that formed before our sun existed. We have launched spacecraft that are even now crossing the interstellar boundary, the first human-made objects to enter the space between the stars. We did all of this from the surface of a pale blue dot that, from the right distance, cannot be seen at all. There is a particular kind of perspective that comes from understanding your smallness without being diminished by it. It is the perspective of someone who has stood at the edge of something vast, an ocean, a mountain range, a night sky in a dark place far from any city, and felt not the crushing weight of insignificance, but the quiet expansion of awareness that comes with genuinely encountering something larger than yourself. The Earth is small, objectively, measurably, incontrovertibly small, in the context of the universe we have explored tonight. A grain of sand on a beach of unimaginable extent. But it is the grain of sand on which consciousness arose, on which matter organized itself over billions of years into forms complex enough to look back at the universe and ask questions about its nature and extent, on which language developed, and mathematics, and science, and all the other tools that allowed us to conduct the journey we have taken tonight. The smallness of the Earth does not diminish that. If anything, it makes it more remarkable. Consider what had to be true for this to be possible. The universe had to be old enough for stars to form and live and die, seeding space with the heavier elements, carbon, oxygen, nitrogen, iron. That complex chemistry requires. A second or third generation star had to form from that enriched material, with a planetary system stable enough to persist for billions of years. One of those planets had to sit at the right distance from its star, with the right composition, to permit liquid water. Life had to arise and persist and diversify, and eventually produce creatures capable of sustained abstract reasoning. All of that happened here, on this dot, in this corner of this galaxy, in this particular moment in cosmic time. The universe does not appear to have arranged itself with this outcome in mind. There is no evidence that our existence was intended or predicted or guaranteed. It appears to be the result of physics operating over enormous timescales, producing, among the almost infinite variety of outcomes it generates, this one. A world with people on it who can look up at the night sky and wonder. That wondering, that quiet, sustained, patient attention to the question of what is out there and how large it is and what it means, is perhaps the most significant thing our species has ever done. More significant, in a certain sense, than any of our political or military or economic history, because it is the thing that connects us most directly to the universe itself. The universe, in a small corner of itself, has become curious about its own nature, and we are that curiosity. Lie still for a moment with that thought. Let it settle the way the larger numbers settled earlier in this journey, not quickly, but slowly, with patience, the way understanding always comes when it comes honestly. The Earth is small, you are on it, and from here, you have just traced the outline of something almost incomprehensibly vast. Chapter 14. Final Reflections. We began tonight with a breath, the rise and fall of a chest, the familiar weight of a body at rest, the small, manageable scale of a room, a building, a city, a world that felt, in those first quiet moments, like something a person could hold in their mind without difficulty. And then we began to move, outward through the atmosphere, past the thin blue line that separates this world from everything else, past the moon, that ancient companion, hanging at a distance that already stretched the imagination, through the solar system with its vast empty spaces between small, lonely worlds, past the outer planets, into the long silence beyond Neptune, toward the nearest star, still unreachably far, still separated from us by distances that make the solar system seem small. Then further, across the Milky Way, that great river of stars we are forever inside, so large that light takes 100,000 years to cross it, into the local group, where our galaxy and Andromeda and 50 smaller companions orbit each other in a slow gravitational dance that will, in billions of years, end in merger. Into the cosmic web, where galaxies are arranged along filaments stretching hundreds of millions of light years, separated by voids so vast they contain almost nothing. And finally, to the edge of what we can see, the observable universe, 93 billion light-years across, containing 2 trillion galaxies, bounded by the oldest light in existence, beyond which the universe continues in ways we cannot directly observe. It is a long journey, and we took it slowly, the way a journey of this kind deserves to be taken. What do we bring back from it? Not certainty. The universe at its largest scale still contains enormous mysteries. We do not know whether the universe is infinite or finite. We do not know what, if anything, exists beyond the observable horizon. We do not know whether our cosmos is one of many or the only one. We do not know whether consciousness is a rare accident or a common outcome of the universe's tendency to organize matter into increasingly complex forms over time. These are open questions. They may always be open questions. And there is something quietly right about that, about a universe that remains at its edges larger than our ability to fully comprehend it. A universe that, no matter how carefully and patiently we measure it, always has more to reveal. What we do bring back is perspective, a recalibration of scale that, if we allow it to, gently rearranges our relationship to the concerns and preoccupations of everyday life. Not by making those concerns seem trivial. They are not trivial. They are the texture of a human life and they matter. But by placing them within a frame large enough that the edges of the frame are no longer visible. The things that feel urgent tonight, the worries and plans and small anxieties that accompany a human being through their days, these are real. They are yours. They deserve your attention in their proper time and place. But they exist on a world that is, by the most careful measurements our civilization has ever made, a small and fragile and extraordinarily improbable place in an almost incomprehensibly vast universe. That knowledge does not make your life smaller. It makes it stranger and more interesting. It makes the fact of your existence and your consciousness and your capacity to wonder about any of this into something that is genuinely remarkable rather than merely ordinary. The universe is very old, approximately 13.8 billion years old. You have existed, in your current form, for a few decades at most. In the context of cosmic time, that is less than a blink, far less. And yet, in those few decades, you have experienced things the universe has never experienced before in quite that configuration. You have had thoughts no one has had in exactly that form. You have perceived the world through a particular arrangement of matter and experience that is, in the most literal sense, unique. The universe makes stars by the hundreds of billions. It makes galaxies by the trillions. But it does not, as far as we know, make beings who can contemplate their own smallness with equanimity and curiosity very often. That may be rarer than stars. It may be rarer than galaxies. You are here, on this quiet evening, having traced the outline of the universe from the inside, having followed its scales from the human to the cosmic and back again, having let the numbers settle one by one, like sediment drifting slowly to the floor of a still, deep lake. The universe is very large. You are very small within it. And the fact that something very small can contain an awareness of something very large, can look out at 93 billion light-years of space and somehow hold that scale in a mind that occupies a few cubic centimeters of biological tissue, is perhaps the most astonishing thing in all of what we have explored tonight. The James Webb Space Telescope continues to look outward, its golden mirror floating in the cold of space, collecting photons that have been traveling toward us for billions of years, will continue to reveal new things, new galaxies, new structures, new puzzles that will take decades to fully understand. Every image it sends back is another small extension of our reach, another rung added, slowly and carefully, to the ladder of human knowledge. And the universe continues to expand, quietly, in every direction, at every point in space simultaneously, The fabric of space itself stretches outward, carrying galaxies apart, deepening the voids, extending the distances that light must cross to reach from one corner of existence to another. It does not rush. It does not pause. It simply continues, as it has for nearly 14 billion years, indifferent to whether it is observed, unchanged by whether it is understood. But tonight, from a small planet around an ordinary star in a quiet corner of a barred spiral galaxy, it was observed, and some small part of it was understood, or at least approached with patience and attention, and a willingness to sit with the numbers until they began, slowly, to mean something. That is enough for tonight. Let the scales recede now. Let the billions of light years fold back into the quiet of the room around you. Let the galaxies return to being points of light, if they were ever anything else from where you are. Let your breath become the largest thing again, the rise and fall of a chest, the warmth of the air, the familiar weight of a body coming to rest.